Among the first concepts we talked about in this class were the states of matter. While at the time we gave you placeholder definitions based on properties, definite shape, definite volume, and the like, we're now equipped to give better definitions based on atomic and molecular interactions. To do this, we need to define the ways that particles interact, which we do with the kinetic molecular theory of matter, which has 5 basic assertions. First, matter consists of tiny particles, typically atoms or molecules, or sometimes ions. These have definite sizes that don't change. This seems exceptionally straightforward now that we know that atoms exist, but the roots of this theory were in Daniel Bernoulli's 1738 publication of Hydrodynamica, which came 170 years before Einstein and Perrin gave convincing experimental proof of atomic theory. The next assertion is that particles are in constant random motion. We already talked about this a little bit with diffusion and effusion. A particle in motion always has kinetic energy. Particles also have potential energy that will either push them apart or pull them together. We talk about this mostly as intermolecular forces, the forces between molecules, and usually we're talking about the ways that they pull molecules together. Since temperature is a measure of average kinetic energy, the higher the temperature, the higher the kinetic energy of an average molecule goes. And finally, particles can transfer energy back and forth by colliding. Not actually physically with their nuclei, but by getting close enough that their electrons repel each other and they bounce off each other. This theory allows us to redefine states of matter in terms of their relative kinetic and potential energies. Remember, kinetic energy is related to temperature, and that the major component of potential energies are their intermolecular forces that are pulling those particles together. So when kinetic energy is really low compared to potential energy, that means that the energy of motion is significantly less than the forces holding the molecules together. This explains why solid particles are about as close as they can be, and they can't change very much with temperature. The kinetic energy is way less than the potential energy. If our kinetic energy and potential energy are close, the particles can start to flow freely around each other, but are still held close by intermolecular forces. This explains why liquids lose the definite shapes of solids, but are still relatively dense and have consistent volume, because they have energy of motion approximately equal to their attractive energy, the potential energy. Finally, gases consist of particles that are very far apart, which makes potential energy almost negligible. The kinetic energy, the energy of motion, represented by temperature, is much higher for gases. And so we see for gases, kinetic energy drastically outweighs the potential energy. It's important to remember that when we're talking about temperature, we're talking about an average kinetic energy, not the kinetic energy of every single particle. Because the particles are constantly colliding and exchanging energy, some are temporarily getting much less energy than the average, while others are getting more. This follows what is more or less a standard distribution. Of course, if we increase temperature, the average kinetic energy will increase, and therefore the speed will as well. But we also see that the shape of that distribution changes because kinetic energy is proportional to velocity squared. The higher the average kinetic energy, the more dispersed the velocities, and therefore the kinetic energies of any individual particle will also be. The mass or molecular weight of a molecule will also change its distribution. Smaller molecules, like helium, will have higher overall velocities, since their mass contributes less to their kinetic energy. As molecules get larger, as we see moving down the noble gases to neon, argon, krypton, and eventually xenon, the mass is also a higher percent of the kinetic energy, and the velocities become lower and less widely distributed. Now that we've talked a little bit about kinetic energy that can pull particles apart from each other, let's talk about a few ways that we see potential energy that pushes them together. Pressure, of course, increases collisions between molecules. If a molecule is trying to break free from another molecule, but is constantly getting hit from the other side by particle collisions, it makes it much harder. For this reason, pressure can shift the boiling and melting points of substances to higher temperatures and higher required kinetic energies. So pressure is a form of potential energy. As we indicated, intermolecular forces, that's forces between molecules, are also a source of potential energy. The stronger these attractive intermolecular forces are, the higher the boiling and melting point, and the more kinetic energy that's required to separate them. We've talked about a number of interactions between particles already. ionic interactions are the strongest of our intermolecular reactions, having electrostatic potential energy that increases with charge. We can also have hydrogen atoms that are shared between molecules. We haven't talked much about this yet, but it occurs most readily when we have electronegative atoms bound to hydrogen, like HO, or HN, or H with any sort of halogen. It distinctly does not mean when any hydrogen is bound to anything, only when hydrogens bridge molecules. In Chapter 4, we also talked about how molecular geometry can be used to identify molecular dipoles. Stronger dipoles give stronger interactions, but these are usually less strong than the hydrogen bonding that bridges molecules. Even if none of these forces that we just listed are apparent in a molecule, electrons can temporarily move to one side or another of a molecule, allowing for a very weak interaction between particles. This happens to all particles, but is significantly less strong than dipoles on a per interaction basis. Very large molecules will increase the number of dispersion forces as they have more locations to interact. By having at least a basic understanding of the forces that hold molecules together, we can begin to see why ionic compounds, which interact more strongly, tend to be solid, while molecular compounds, which typically have some combination of weaker interactions, tend to be liquid or gas. These interactions between molecules also change the way that particles behave in the gas phase. If particles have significant intermolecular forces, they start to act a little sticky when they collide. If particles are large and irregularly shaped, the volume between molecules make up for a smaller percentage of the actual volume. For this reason, even the most simple molecules are not completely ideal. The graph displayed has pressure in atmospheres plotted against a compressibility factor, Z. The compressibility factor is a measure of how the actual measured volume of a mole of gas, V mole, compares to what we'd expect from the ideal gas law. All these gases are small and pretty weakly interacting, so they're among the most ideal gases possible, excluding helium and neon. And they're mostly ideal at reasonably low pressures. Note the scale on this chart is from 0 to 1,000 atmospheres. But as pressure increases, the interactions between molecules and the size of the molecules matter much, much more. In the late 1800s, Johannes Diederik van der Waals noted that gases didn't actually behave completely ideally, and posited that there could actually be interactions between molecules in the gas phase, and also that the size could matter in the gas phase. For this reason, some people call the collection of possible intermolecular forces van der Waals forces, and the approximate size of a molecule the van der Waals radius. What we care most about is the equation that van der Waals came up with to explain gas behavior more accurately. Instead of simply using P in the ideal gas equation, van der Waals asserted that molecular attraction would make molecules feel less pressure than expected, as they'd stick together and reduce the overall pressure at a constant volume. Van der Waals used an empirical value of A to explain the attraction for each molecule. Of course, the more molecules there are, represented by N for moles, the more we'd have them stick together and the more this factor would matter, which is why we see N squared in the correction for molecular attraction. On the other hand, if those molecules are dispersed over a large volume, that volume makes them less likely to interact, which is why we see volume squared in the denominator, decreasing the contribution of this correction. Similarly, instead of simply using volume, van der Waals suggested that each gas molecule had some amount of space associated with it. This correction is indicated by adjusting the volume and subtracting NB, N to indicate the number of moles, and B to give some indication of the size per mole. The result is that the larger molecules will result in the system feeling like there is less volume available and pressure would increase. This comes through in unexpected ways in medicine. Whenever we breathe in, we're adjusting the volume of our lungs with our diaphragm. This changes the pressure so that it's either lower or higher than ambient temperature. But this doesn't change as much as you'd expect. The difference is only about a few torr, less than 1% of an atmosphere. In addition, our lungs are not wide open vessels, but instead consist of airways that gradually become more and more constricted until eventually forming the majority of space with incredibly small bronchioles. This means that all the gas coming into our lungs comes in through very small volume tubes, and the interactions with the surface of those tubes will change the flow of the gas. The greater the attractive forces are between the gas molecules and the bronchioles, the more likely the molecules will get slowed down on the surface and create what's called turbulent flow, shown on the bottom left. The less attractive forces are between the molecules in the bronchioles, the more likely the flow will be laminar, shown on the bottom right. Laminar flow delivers gas far more efficiently, and so it's essential that our bodies adjust to try to make this happen as much as possible. When a baby's body is developing, they produce a collection of compounds called human lung surfactant to coat the bronchioles. This reduces interactions between the bronchial surfaces themselves, but it also reduces interactions with the lung gases. Human lung surfactant is developed pretty late in pregnancy, which is why the lungs get so much attention in neonatal units. Human lung surfactant is only one side of how molecular attraction comes into play. If someone is having trouble breathing, they're often put on a ventilator. What the body actually needs from air and from that ventilator is oxygen. Oxygen makes up about 21% of air. Often the pressure of the air is increased to increase the partial pressure of oxygen and help force the lungs open. However, giving pure oxygen has all sorts of negative side effects. For the tiniest patients with the tiniest lungs, doctors will sometimes choose to replace the 78% or so of air that's nitrogen with another gas that has a lower correction for molecular attraction. So more oxygen can be delivered by more laminar flow. What gas from this list do you think would reduce molecular attraction the most? Helium is by far the most ideal gas and has the lowest value for molecular attraction. When my then 2-year-old son was hospitalized with reactive airway disease 4 times in one summer, the doctors put him on what they call Heliox, a mixture of helium and oxygen, to improve the laminar flow of oxygen and helium into his lungs. And you might imagine what it did to the already high register voice of a 2-year-old. Adorable.